I know that in the past I've harped on phosphorus quite a bit. Last year's NREC, I spoke about our work on updating P and K RECs from our on-farm network trial on legacy phosphorus in soils and sediments. This year my plan is to go the other nutrient and talk about nitrogen. And what I want to do is to point out what our current projects via NREC are suggesting as potential blind spots. Blind spots because these might be sources of N losses where there are small gains to be made on N loss reductions, but in aggregate, these can be appreciable. So the goal is not going for the major loss pathways, but the little bit here and there that, like your bank account, if you round up to the nearest dollar, that spare change begins to add up. So can we find enough spare change of nitrate loss that in aggregate might be meaningful? And I'm going to walk through 5 different examples of where there's reason to think that it might matter. Maybe it turns out that it doesn't matter, but it would be good to know. So that's these overlooked pathways and then potential solutions, not to solve the nutrient loss problem per se, but at least to dig our teeth into what would it take. So first, a big thanks to those that make this work possible. This is across all the projects that you'll be hearing about who's involved in different ways. I'll begin with the N cycle, highly simplified, very agronomically centered here. And what I want to point out is we typically think of our N inputs in this way. We add UAN, anhydrous, we produce ammonium, which then oxidizes to nitrates. And that nitrate really is what we think of, and the data does indicate, is the major loss pathway of N. There's a little bit loss atmospherically, but agronomically, we're talking just a couple of pounds per acre. So we've heard all morning some really nice work that demonstrates the poundage, the pound per acre of nitrate N being lost. So this is a pretty good agronomic cycle of N. As a biogeochemist, let's layer on a bit more going on here. So there's additional pathways that merit attention. For example, there could be surface losses of nitrogen. I know phosphorus gets all the attention for surface loss, but as you'll see today, we are losing a few pounds of N per acre as surface runoff. Over 1 million acres or more, that begins to add up. There's also sediment that contains organic nitrogen that will then downstream mineralize into ammonium and thus into nitrate, which, as Lowell had said this morning, that's also happening in soils, and it's partly responsible for what's hitting our tiles. We also have technologies that attempt to arrest or at least to retard certain steps in this process, like inhibitors. And we also, I think, have overlooked sources of N inputs that we don't really think much about. Again, small overall compared to the main inputs, but across many acres in aggregate can be appreciable. So then the goal is to talk about these 5, shown here with blue circles, these 5 major overlooked pathways of N loss. What are the gaps? What does the evidence suggest on how much? And what can we do to try to decrease these losses? Okay. So let's begin with inhibitors. I'm going to begin here because I think it well illustrates that it's always good to be a heretic and question assumptions. And the assumption that I'll be questioning here is that's present in the state NLRS, which makes this assumption of a 10% nitrate N loss reduction by use of an inhibitor. So this is not just unique to our states. Other states in the basin also use this, and they also agree on a 10% reduction. I think they were all talking to each other in the same room, so it's the same number. So then we know that these inhibitors work for 2 things. They on average decrease N2O gas emissions. So for things like 45Z, for climate smart assessments, inhibitors work. They yield, on average, a net benefit. They decrease N2O. And for yields in very wet soils, there's good evidence, especially down south, that these can increase yields as well. It's complicated. It depends on the year. So we're not talking about these other benefits. We're talking about, do we see nitrate out of tiles decreasing when we use an inhibitor? Very specific question. So if we look at what's out there as part of a new project that we have to look at the BMPs in the state plan, we are trying to find publications, peer-reviewed, that look at tile losses, these loads that we've heard about this morning. We're not looking at recovery of soil N or lysimeters. These are rough estimates, but they have a lot of issues. So there's 3 site locations that have ever been studied in the entire Gulf Basin that look at inhibitors and effects on nitrate loss by this standard. And these are in really 3 states, in Douglas County, just south of us, and then in Iowa and Minnesota. 25 treatment years, like site years, except there's 3 sites, so treatment years. So the entirety of the MRB states that assume this % reduction are based upon 25 site years. It's not actually based on these studies, but this is all we have out there to assess it. So let's look at this data. 25 site years is not nothing. This is hard data to get. What do we know about inhibitors and nitrate and loss? A few things. All studies are over 2 decades old, or 2 decades old this year. And because of that, they use pretty low N rates. We know that this rate is going up, as Dr. Jones had talked about this morning. 20 years ago, they were looking at these rates of 120 to 140 pounds of N per acre, with N-Serve as the main product. So what do we see here? To interpret this graph, I want to walk you through these quadrants. The y-axis is the delta in tile and loss, a delta, right? So if it's a negative, that means that we're decreasing, that's a good thing. If it's a positive, that means we're increasing nitrate loss. On the vertical, in going left to right, we've got corn yield, delta. We want that to go up or at least stay neutral. So to map out these quadrants, bottom right is what we want, right? We want yields to go up and tile losses to go down. This would be the miracle. We also have the opposite, the complete failure, where yields go down and we increase tiles. You might laugh, but there might be data out there. And then we've got these mixed scenarios that are simply trade-offs, right? Yield versus loss trade-offs. What do we see with the actual data, the 25 treatment years? Quite a spread. We do see the worst case and the best case. And the % of study treatment years that fall into each quadrant, into each scenario are shown here. If we add this up, we find that roughly a bit more than half of all studies see an increase in tile when an inhibitor is used. And then we find just about under half that find the opposite. So pretty messy data, but that's what it looks like. What about that assumption of 10%? Well, if we think about that dotted line on this graph, that would be the one-to-one line. So we have on the x-axis what's being assumed. The measured, if it were to agree with that assumption, would be a perfect line on the dotted line. Some points are above and some points are below, but overall, depending on how we look at outliers, we are seeing a 3.4 to a 2% loss reduction on average. The median's a little bit higher, but the point is that we're that we are achieving a 5% reduction at best with the median, with all the data. And if we're a little bit more careful, we're talking more like 2%. So if we think about the math, these were all done with 120 to 140 pounds of N per acre. That's about 2.5 to maybe 6 pounds. With today's rates, if we assume that this scales, we're talking 6 to 8 pounds of N per acre. So why am I harping so much on this? Well, this is an important magnitude. We give a lot of credit to what inhibitors can do. It's an official BMP, but we're maybe achieving on average a 5-6 pound nitrate N decrease per acre. What are other similar magnitudes of losses or that are as much or greater that we could potentially achieve? So one that would come to mind would be MAP and DAP. We're certainly applying more than 5 or 6 pounds of N via the P application. So if we add this up, this is a quite appreciable blind spot. The gap here is pretty simple. Is the MAP and DAP nitrogen, the ammonium, is it part of what we see coming out of tiles or as runoff? Simple question. If the answer is yes, it probably is yes as a qualitative. The better question is how much? How many pounds per acre? So the second question, the second gap that I think matters as much is, can we manage this? Is it worth our time to try to think about capturing the fall applied MAP or DAP N? So as a bit of background of why this might matter, if we do some simple math, assume half of the acres that go into corn in the state, so roughly a quarter of all acres, ballpark. If half of the corn acres are getting fall applied DAP at 200 pounds per acre, that's about 200 million pounds of nitrogen This is ballpark math, which exceeds our reduction target by 11%. So as a theoretical, if you were to somehow not avoid any loss, if there is loss of that, then that could be a big bite being taken out of our nitrate reduction goal without messing with the main N rate for corn as UAN or as anhydrous. So again, a theoretical, but this is not a little bit. If we think about the pathway here, going back to the biogeochemistry, we add DAP or MAP, it dissolves, it makes ammonium, which can be blown off. That's unlikely in our pHs. But really, we find from data that we rapidly nitrify following rapid dissolution. Within days of application, if it's wet and warm, like this fall, you have converted the MAP or the DAP-N into nitrate. And then it's susceptible to loss, really as leaching loss is the main concern. So there's trade-offs here, right? Fall, applying ammonium phosphates makes sense for lots of good reasons. It's practical, the ground tends to be less wet, you get it done with, etc. It also, in some years, might be colder compared to spring applied, and so there's a trade-off of is spring or fall better for this reduction of the N? We're not really sure yet. So I don't have answers here, and really no one has answers because, as we found from this study, that there's exactly 0 evaluations of the fate of nitrogen from MAP or DAP when it comes to leaching out of the field, not recovery in the surface soil. So this is a larger issue. 8% of all of the nitrogen that enters cropping systems in the world, 8% of Haber-Bosch-N is as MAP or DAP, and we don't know what's going on with it. So this might be a good example of low-hanging fruit. To this end, we have a few field sites with Eric Miller and Dan Schaefer and on campus. Approximately about 70 tiles that we are monitoring to understand the fate of the fall versus spring applied MAP or DAP. Can covers, can winter wheat, can inhibitors, I know that I just talked about them in not a great way, can inhibitors perhaps move the needle in combination on reducing this blind spot? Okay. Another one that we've talked about and that we heard this morning, Lowell especially did a great job emphasizing this, would be how much organic matter turnover can contribute to nitrate losses. This is not a new idea. This study from 1844 is arguably the first publication that documents that there are appreciable losses of nitrate through tiles. This is England in the 1800s, even in unfertilized soils. And that was the real takeaway from this study. The point that they're trying to make is that there's native capital, there's natural nitrogen that's being lost. And so for them, it was still a concern as it is for us today. One issue with this is that BMPs have a pretty high baseline if we think about the targeting of nitrogen. You know that you have X pounds coming out of the tile, and to me, it's a very salient question that I'd argue is on par with flow normalizing losses. We have to normalize for what we're going to lose from organic matter. There's a philosophical debate here about how much should we be having the BMPs targeting the nitrate from organic matter as much as from the fertilizer? And that is a good question. They arguably can do both for some, like covers, maybe not for others, like the 4Rs for nitrogen, obviously. So the question then is, what would be a reasonable background of nitrate loss, especially given the divergence of soils across the states? The northern black clay soils will lose more nitrate than the southern soils in the same way that we lose more P down south because of more erosion, right? So how can we get good numbers on what would be a, quote, acceptable or let's say likely background loss? I think this is a really important next step for the state NLRS. So to illustrate the importance of this, let's go on farm. Let's take the land grant to the field, get off the campus plots, which have their place, and try to get over acres that are commercially managed. So for this, I'll bring you to the north central part of the state where we've got this tri-county network totaling over 1,200 acres and 22 fields that we monitor continuously for tile flow. As we do for the campus site alma mater plots with 64 tiles, we're doing this for much more acres on private farms. This has been going on for about 4 or 5 years now, part of an NREC and a few other projects. And this is really a farmer-led project. These farmers from Bureau County came to us and said, can you help us figure out how much nitrate's being lost, and then can you benchmark or try to document the efficacy of our BMPs, covers, spring application, etc. This was featured in the furrow, the John Deere print for next month. It's not out yet, so you all get a VIP preview of that. So this, I think, is a great example of how we need to go to the field because, as you'll see, how a BMP like a cover crop behaves is more variable. And there's insights there for how we might think about the hot spots of loss that drive the average numbers. So let's begin with a bit of background here of just how much water is being discharged. This is relevant to the end thing in just a second. So in these counties, we find over the last 2 water years, we had a lot more precip in 24, 34 inches a tad dry for this area, and about roughly 1/3 of that was exported by tiles in magnitude. The drainage coefficient was 0.32. Last water year, we found across these 22 fields that there was a lot lower drainage coefficient, though there was only 5 inches less of precip. So we had 1/3 less drainage. It's complicated because we've got groundwater that swells up, as Dr. Yu talked about, but you get the idea. So a small change in precip, a big change in tile flux or flow. 45% less tile, to be exact. So we have this disproportionate, this oversize effect. What you're seeing here are 49 site years. So every site year is one field from 20 to 80 acres, monitored real time, 15 minutes for flow, and then we analyze the water samples for nitrate to calculate load. And what I want you to focus on really is on the nitrate end loads right here. I've broken it up by corn versus soybean. And if you look at the average values, those letters in black, we're losing about twice as much nitrate N across these commercial farms, over 1,000 acres. We lose about twice as much under corn than under soybean. But we're still losing under soybean. And Lowell had talked about a few of these examples or reasons for this. What I want to point out too is that this was reflecting a pattern of precip. Most of our corn years were in the wetter year, so there's a confounding factor. That's the reality of on-farm work. But a lot of our tile nitrate in this on-farm context, as we've seen from research farms to small plots, flow drives loss. Hence Dr. Peng talking about we must normalize to add a dimension to the current approach. One thing that I want to point out is this outlier, not an outlier, it's real. This one field lost 80 pounds of N per acre of nitrate under soybean. And I know that this farmer is doing no-till. He does cover crops. He's very careful with his nitrogen. He's adding under the MRTN using biologicals to make up the difference. This is a person who cares about their nitrogen loss, who's part of the project. And this field lost quite a bit because look at the flow from that field. So it goes to show a few things we should be careful with, as Lowell had said, that just because there's nitrate coming out, it's not from fertilizer. This is a really good example of the extreme that illustrates the lesson that we can lose a lot of nitrogen with everything being done right. Cover crops, no tillage, and it's under a crop that receives 0 nitrogen. So this is an example of how organic matter is very important to account for. The noise is, I think, a really key question. How do we, for the NLRS and for BMPs, begin to account for the variability and what the background nitrate loss is? And that has to be answered in order to inform federal ideas and policy, as well as how we monitor progress. So let's look at some cover crop data, the same 49 site years from these commercial fields. And now you've got cover and no cover crop. We see about a 1/3 reduction, about 4 pounds per acre with the cover compared to not. And these covers ranged all over the place. But they're grass species. They're not leguminous cover crops. And if we look at the water load, we find that there's also this association of lower water out of tiles with the cover crop. Again, the weather could confound this, that we had the covers in front of soybean going into the more dry year, but there is evidence that cover crops like winter wheat can reduce water moving down. They're moving water up. So we should think about how we manage nitrate via the hydrology by getting water not from reaching the tile. The more that the water evapotranspirates through things like cover, wheat, residue harvests, for evaporative purposes, the more that we avoid water dragging down the nitrate. So indirect association here, but it's worth looking at. So note these averages, note those little tiny dots in gray, that's the real data. The average can be misleading when the distributions are so wide. And here's a good example of this. If we look at the same data and we look at the distributions, which would be the shaded areas on top, I've shown here the median. So you just saw the averages. The median losses of nitrate N per pound per acre were 0.7 with covers. 0.7 pounds of N per acre lost through tiles, and 3.1 without the cover crop. And you're thinking, Andrew, you just said it was 15 without covers and 7 with covers. Yeah, that's the average. Look at the right-hand side. There's a few fields that lost so much that the average was dragged up from 3 without covers to 15 without covers. So there's an important lesson here is that the median reductions of a BMP like cover crops might actually be securing a greater reduction. So right now, if we see the average data, we decrease nitrate by 36% with covers as a mean, as an average, but the median reduction is much greater. It's more than double that. So there's an important thing here because of the nature of these right-skewed distributions where a few loser fields lose a lot, we tend to have better median reductions than means. I don't know what we do with that next, but that hasn't really been talked about in these discussions. Now again, these fields that lost a lot, like the 80 pounds per acre under soybean with no-till and covers, that's not to say that these farmers should be targeted, but rather that with doing everything right, you might still see one field lose 80 pounds, and that brings up the average. So for modeling, for policy, and then how we credit a BMP, the percent reduction, the range is going to be pretty important to account for. These are the averages. They're much higher than the median for that reason. Okay, so another theme that relates to organic matter, nitrogen, and it can transform into ammonium and then into nitrate would be sediments. And I'm going to go back to the P theme, I couldn't help myself here, on sediments and phosphorus. So this is data from our now in the 3rd year network of stream bank erosion monitoring. We're in year 3. Meaning that every 6 months we measure the bank rate of recession, we measure the amount of nitrogen and phosphorus in the stream bank. What you're seeing here is over 2 years, the last 2 years, the poundage, the amount of sediments that were loaded into streams across the state. We do this at 2,500 locations across the state, 2,500. And what we found was that in 24, we had 53 billion pounds of sediment from stream banks. 53 billion. We had 15 billion, so 3 times less in 2025, much drier. So insight is a lot of variability based on precip from year to year. This is why doing these erosion projects for decades like Iowa is useful to give us some insights. Now, sediments contain phosphorus naturally as well as some amount of nitrogen. The question then is how much is this for N and for P? So for P, if we do the math, it's about 25 million pounds of P were loaded by stream bank erosion in 24, and about a third of that, so 7 million pounds of P, compared to the baseline of 34 million pounds. So the relative loading contribution can vary quite a bit. If we think about the apportionment of the current state plan, 48% is non-point source. This could mean that in a low losing year, we're losing almost all of the non-point source equivalency from stream banks, and in some years, it's all of it. So there's a lot of interannual variation with implications, immediate implications for source apportionment of phosphorus. So this is P. There's N that we're measuring in these sediments, but there's a simple question of how much. Probably less proportional to nitrate from ag landscapes, but still appreciable. So just like the MAP or the DAP, all of this in aggregate begins to add a couple pounds of N per acre. These are opportunities for reducing losses. Speaking of which, one that's also tied to sediments and involved with runoff run by Mariana from our lab is surface runoff losses of nitrogen. This began as an NREC project focused on phosphorus losses, and we realized, what about N? Is it appreciable? It's a very, very simple question. And so what we do is that we are trying to understand whether there is a gap in the state NLRS, which does not currently account for surface loss of N. It's all vertical. It's all through tiles. Why does this matter? Well, down south, there's more rolling terrain. You could argue that there's some more potential for nitrate and ammonium loss. And up north, where it's flat, there's just so much more organic N that it could matter. So if there is a gap, then how much can we move the needle on it through BMPs? Can we double credit? Could a cover crop have benefits for surface and subsurface losses, for example? So for this, we look at runoff continuously. Every rain event, every runoff event, we do a sampling over 70 plots across the state. So to date, I think the number is over 5,000 samples collected. It's probably more than that. There's a poster that you can see for the details. So this is important because we lose most of our runoff sediment and P and maybe N in 10% of the events. We have to go there every single time over years and years. So for this, we have two sites that I'll focus on. One is here in Champaign on the flat and black. This is sort of the best case. We have minimal rates of sediment and runoff as a volume in these flatter landscapes. We're talking less than 2% slope. One site shown here is about a mile away. And then I'll go to the southern site that's more sloping, down by Franklin County. So this is the best case. And we have higher OM, higher N-loss potential. What do we see here? Well, let's first look at by tillage practices how much we are losing for sediment. We're losing roughly 1/3 less sediment when we have no-till compared to chisel till on the flat and black on a 1% slope. The total amount in terms of poundage is about 320 pounds versus 1/3 less. Not a ton. We see some parts of Iowa are losing 5 to 8 tons per acre. We're seeing about 0.15 tons per acre. So this is already a good example of how slope dictates erosion rates, just like flow to tile dictates nitrate losses. If we think about how much of this is explained by the runoff, only about half of the soil loss is due to the water amount. So we see less water coming off the plots with no-till compared to chisel, but there's a half that's not really explained there. Now, this could be lower with cover crops and weed, and that is the topic of a current NREC we just began. No results yet, so stay tuned. So that's the amount of sediment loss. What about the amount of dissolved nitrogen? This is ammonium, this is nitrate in these same plots. We're seeing about 1 pound to less than 1 pound per acre of nitrate N, and then about the same, a little bit lower for ammonium N. We see that with no tillage, we get lower nitrate loss, a little bit higher as a mean for ammonium. A few points here. These behave differently. That might reflect the sources of fertilizer, SOM. We do still see net loss reductions of no tillage. So it's an extra pound per acre that we could credit no-till for the reduction in N. Now, you might be sneering at 1 pound of N per acre, but then again, inhibitors are giving us maybe 2 or 3 pounds per acre. We stress those a whole lot. Why not no tillage, double dipping its benefits for the surface loss pathway? And this adds up over time. So the good news is that we're not losing a whole lot of inorganic N through surface loss in these flat soils, but it's something. This is best case. So let's go down south where it's more rolling, where there's documented higher rates of erosion. And here we see across zero fertilized control, zero when it comes to ammonium phosphates in gray, and then on the right-hand side, you've got 3 colors that show MAP or struvite or a mix of these. What we find first is that there is comparable inorganic N loss as runoff at the southern site with much higher slope than the flat and black. That was a surprise to us. So we're still losing about 1 pound per acre per year because this is a 2-year cumulative loss. So that's about the ballpark number. We also find that we have increased losses equivalent to about 3% of the nitrogen applied as MAP, as DAP, as struvite. So if we are losing N from MAP and DAP, it seems like a minor proportion is by the surface as runoff. If we're losing more from MAP or DAP, it's going to be through the subsurface by leaching. So there's a partial answer to our question. This is good news. We're not hemorrhaging nitrogen off of runoff, but we checked it out. There's about pound per acre of N. So to summarize all this, we lack strong evidence on these inhibitors. There's a couple typos here, sorry. We lack really strong evidence for the current assumption of our inhibitors decreasing N loss by 10%. We need to look at higher rates and through the standard of tile drains that we monitor. That would give us more confidence in ascribing that reduction. MAP and DAP is an opportunity to decrease N losses. Surface losses are minimal. We're talking maybe half to 1 pound from the fertilizer. Maybe there's more being leached. We'll find out in the coming couple of years. We're losing N by organic matter. We've heard about this morning. What I was trying to do here is show you how at the commercial field scale, that amount can be enormous. 80 pounds of N per acre from organic matter in one extreme situation. So there needs to be, I think, a bit more work on, by soil types, documenting what the baseline background could be. And those give us more regional targets to reduce. There's likely very high loading in terms of total millions of pounds, but percent lower, likely contributions from sediment. Our on-farm work shows that flow matters most. This is a duh thing, we know this, but it gives you nuance in how much that can vary by field, and it will drive field differences, including the median being a lot lower than the mean. So there needs to be a way to account, I think, for these right skew distributions. And then the surface pathway that we've been investigating, we know it's appreciable for phosphorus, 1 to 3 pounds of P per acre. For N, it's about the same, 1 to 3, really 1 to 2 pounds of N per acre. So I'll end on this. Last year, I gave an update on the example of an impact that our lab is doing with the support of NREC. We have published 39 papers so far. I point this out for a few reasons. This is directly used by policymakers. A few of us were in DC 2 weeks ago talking with the with the federal EPA. And the point is that we can use these kinds of publications that are the result of funded NREC work to show policymakers things like legacy P is a thing. It's now in the vernacular of USGS and US EPA because of this kind of work. This work also goes into direct farm applications, handbook updates, conservation updates, for example. And I think most importantly, or as importantly, is it helps guide better policy. And as Dr. Jones had pointed out, we can use these funds to bring in more money from outside of the state. In the last 2 years alone, our group has used the NREC investments to bring in $4.2 million, broken up over these different funders. I want to point out that a lot of federal sources like FFAR, they require a non-federal cash match. So NREC dollars are not federal. So when the feds say, if we give you $1, you come up with a second dollar, NREC is uniquely positioned to enable those cost matches, to double the money that comes in. So thank you for the investments in the research. It really goes a long way. That's all I got.